Mr. Wizard!
Oh, hi, Alan. Come on in.
Hi, Mr. Wizard.
Hi. I'm practicing. Come on, you come on
Practicing?
around. Yes. You see, here's a magnifier on a stand,
Yeah.
and you look through about that far away or so, and tell me what you see.
All right. Well, I see a big eye.
Yeah, big eye.
Right side up.
And notice what happens when I go back. Gets bigger.
It gets bigger, yeah.
Now what happens right here, though?
It's fuzzy. It's out of focus.
Yes. And then what happens when I go back?
Now you're upside down.
Yeah.
And you're getting smaller.
You're getting smaller and smaller and smaller as I go away, right?
Yeah.
Okay, now I'll come up more quickly and you'll see. Just the reverse happens,
Yeah,
right?
now you're okay again.
Well, now you can do these, do that sort of an experiment at home, and with this simple convex lens, that's what all that is, a magnifying glass, we're going to investigate some of the principles involved in ordinary optical pieces of equipment that you've seen around all over the place. So with a simple lens like this, I think you can understand at least the principles behind some very complicated ones. Come on over here, let me show you.
All right.
Here they are.
Uh-huh.
Now, you recognize what that is?
Well, that's a camera.
That's a camera, and I have taken the lens out in front so that I can project the light through here so that you can see there's the picture?
Yeah.
Upside down.
It's upside down.
And notice it's quite small.
Yes, it is.
I have already mounted it in the frame. That's not, very common. So there's a picture, upside down and smaller. Quite small, right?
Yes, very
okay,
small.
that's one of the optical pieces of equipment. Now here's the next one. Now in order to use this is meant to be used in a dark room. So I'll turn out the lights and get it very dark, just like in a dark room. I'll turn this on, and now you look down here and see what you see.
I see the same slide.
Yes? Oh, wait a minute, I got to turn out a couple more lights. There. Now, you see? Same
Yeah.
slide, right.
It's larger, though.
It's and this, you see, is about 5 by 7 or so. Well, that other one was about 1 by 2, or a little smaller than that. So this is a little bit of a little larger picture, but it's the same picture, but now just a little bit larger.
Yes,
all right?
that must be an enlarger then.
Oh, this is an enlarger, right? Now let me turn the lights back on again. And now, you recognize that.
Yes.
Now you recognize this.
Yeah, that's a slide projector.
Slide projector. Well, let me turn that on. And you see I have a screen over here.
Yeah.
So that here's that same picture again.
That's bigger yet.
Yes, this is about, what, 18 inches by maybe 24 or 30. And you can make it even bigger yet, can't you? By
Yes.
throwing it further away, having the screen further back, so that you can get 3 by 4, 5 by 6, you can get quite big. Okay, well, that's the third optical device. It's a fairly common one. And the other one is up there next to the projector.
The magnifying glass?
Yes. Let me turn the projector off first. Now I have a little, that same little slide set up here. You see it?
Yeah.
Okay, now let's look at it first without the magnifying glass. And you see what
Small.
size it is?
Very
It's quite small. And when I put the magnifying glass, what happens to it?
It becomes larger.
Yes, it becomes larger. Okay, now remember those three those four things, because what you're going to do is try to see the optical principles involved, and it's really all very simple because it's all based on the various cases, they call them, of the convex lens. Okay?
I'll try.
Let's see if you can do it. All right, let's start at the very beginning, however. Come on around over here. And you're going to have to do the same sort of thing that an optical designer does when he designs a lens. And here's your whole design board right here.
Well, what is it?
Well, let me see if I can explain. Here is a lens. See in the middle?
Yeah.
That piece of paper there represents a lens. And it's a lens that has a 15-inch focal length, 15-centimeter focal length. See it? Okay. Now, let's assume we have an object way, way out here at infinity, far, far away.
Okay.
We're going to trace one ray. See that black line there?
Yeah.
That one ray is going to come right through the center of the lens. See, it goes along here and goes right through the center of the lens. And whenever a ray of light goes through the exact center of the lens, it is not bent, like it is in other rays at other parts of the lens. So it comes right straight through and comes out the other side and keeps right on going.
A straight line.
That's one. Now let's take another ray that's coming in here way, way far from infinity and see it's parallel to this ray.
Yes.
Okay, now watch what happens with that one. It comes through here. It goes through the edge of the lens up here, and now it's bent. Comes down here, see, and notice where it crosses?
At 15.
15. That's the focal length.
Oh.
So there's a little left there, see?
Yes.
Okay, now the ray continues to go on out over here. So now this is what happens when two rays of light from infinity come together and they cross at their focal length. You've done that with a magnifying glass in the sun,
Yes, you
haven't you?
get the smallest
Little
spot.
tiny spot. Okay. Well, now, let's take that same object, which I had hidden around here behind the side of the board, like that.
The arrow?
That arrow. The light from the bottom part of the arrow is going wrong through that straight line right through the center of the lens. The light from the top of the arrow, parallel to that base line there, is going to go right straight across here and cross over at 15, isn't it?
Yes.
Okay. But now, the optical engineers, when they design lenses, they trace another ray. They say, let's take a ray that comes from the point of the arrow, out here at 4F, notice, 4 times the focal length, 60 centimeters, and let's find what happens to the ray that goes through the exact center of the lens.
Well, it crosses the other one.
Yes. It crosses it. Would you take that and take that tack and move it up and down so that line just barely touches the pin I have in the center, but so the line is nice and straight, and see where the two lines cross.
There, huh?
About there. Now, this means that the lines of light coming from the top of the arrow, regardless of where they go through the lens, come back and meet right there. That's the point of the arrow.
Oh, I see.
So what, if we were now going to reconstruct the image, we would have a little tiny arrow like that.
Huh. It's
Okay?
smaller.
It's quite small, isn't it?
Yes.
So now, which of those pieces of optical equipment is it? Where an object is quite far from the lens focuses it down to a little tiny image, and it's upside down. Take a look.
The camera.
Yes, the camera. Here's the little tiny, actually, if that was a drawing of me and Irene, the girl who used to come over and do experiments. And so I made a slide of it, and you can see that if we were real people on the other side of it, we're obviously quite little people here.
Yeah.
The image is quite small. So that's and every time you have a camera lens, let me see the camera lens in here.
Mm-hmm.
And you're going to, what happens and when you're at infinity, or way far away, you have the lens like this, but what happens is the people get closer and closer. You see how you focus the lens
Yeah, you
out
have to
further and
refocus
further.
it.
And that, in effect, moves the lens further and further away from the focal point.
Mm-hmm.
Okay, well, that was an easy one.
Yeah, now I'm a cameraman.
Well, there are a couple of other little problems. Let's go back and see what happens, because you can see what happened when I was when I had the object at infinity. The thing was at F, at 15, and now as I brought it to 60, it moved away from F. What's going to happen when I move it to 30? 2F.
I guess it'll come even closer.
It'll keep going further and further toward you over here, won't it?
Yes.
All right, let's try it. I'll move this to 2F,
Right.
which is 30 centimeters.
We have
Okay.
to change this middle ray here.
Okay, now the bottom one stays the same.
Right?
This top one stays the same, doesn't it?
Yes.
But this one right here that goes through the center of the lens isn't going through the center of the lens, is it?
No, it has to be
Okay,
changed.
you better move it down so it is.
Not there.
Okay. Now, can you reconstruct the image at that point?
Yes, it's right about here.
Well, let me. You're not touching the center pin right here.
Oh.
You got to get it just a touch. How's that?
It's at 2F.
Yes. What was the object at?
2F on the other side.
And the image? Is it 2F too? And I think maybe you're a little off. What I'll do is I'll draw a line down here like this. There's the image, right?
Mm-hmm.
How does that compare to the original image?
Looks about the same size.
But it's upside down.
Yeah.
Yes. Well, now you could see how inaccurate this is. This doesn't quite cross, and you'd have a great deal of trouble trying to figure out where that would go. Let's do it the way the lens designers do, by using mathematics. It's very simple.
Is it?
Yes, come on over here. I'll show you. Here's the formula that they write. They say, oh wait, I forgot to say, everything on the side where the object is going to be negative.
Negative.
And everything on the side where the image is, over on your side there, is positive. My side is negative, your side was positive.
Okay.
So they write down this formula. Notice that the object was on my side, so that's negative. And they say, if you put 1 over the distance of the object, and to that you add 1 over the focal length, that will equal 1 over the distance of the image.
Oh.
Now let's see if it works out with what we found over there. I put my side at 30 tonight. That was twice the
Yes.
focal length. I put 1 over 30 plus 1 over 15, which was the focal length of the lens, and that equals 1 over di.
Well, now I have to figure that out.
Okay, now this is pretty easy because all you do is draw a line here, and you can now put the common denominator is 30, isn't it? Okay, and now this is 1.
1.
Minus 1, and that's plus 2. 15 goes into 30 twice.
Yes.
Plus 2 equals 1 over di. So you can subtract that, can't you?
Yeah, it's 30.
1 over 30 equals 1 over di. And now you can simply cross off the top 2 here and say di equals
30.
30. And that's exactly what we found, isn't it?
Yes, that's right.
Very good. All right, now let's see the piece of optical equipment I'm kind of cheating. I'll give you a clue. It's not really here. But what I want
How
to
am I going to find it?
Well, I'll show you what the problem is. Let's say that you wanted to make a slide like this, but you wanted to get it bigger, the image bigger and bigger and bigger. You know, you saw how when we moved the lens out here, it had to go out further and further and further, right? Okay, now if we want to get it bigger yet, we've got to go out further and further and further and further. But they won't go anymore.
Well, get another lens.
Well, that's right. You could get another lens, but you could use the same lens if you just bring it out further. And I'll show you what they do.
That's sneaky.
That's well, I told you
unfair.
that was kind of sneaky. Here is the same sort of camera. Just happens to be a different, newer model. Here's where the picture is going to appear.
Yes.
See? And what I'm going to copy, or what I'm going to take a picture of, is that same slide. See it?
There it is.
There's the slide. Now, I want to make the slide exactly the same size. I want to make the image back here the same size as the slide.
Yes.
Remember, I'm going to copy it in effect. So here's what I do. I set this up like this, and I'll pretend that this is the light that we're going to use to take the picture.
Okay.
And now, notice that here's the object out here.
Yes.
Notice where the lens is.
Right in the center.
And because it's about in the center, the distance between the object and the image, right? The lens is in the center. Now you go around over here and look at the ground glass on the back of the camera. Do you see anything there?
Well, it's a little out of focus.
Okay, I'll hold the bottom part. You move the camera in and out until you get it in focus. You can just move the whole camera. It slides right on the thing. Now you got to go the other way. There you go. Now it's exactly the same size.
That's pretty good.
And this is a device for copying pictures, one slide with the other. Or we can take this out and you could just extend this on and you can get pictures of little insects and whatnot. You got to get that lens far away from the focal point.
That still wasn't fair.
That wasn't fair. Okay, well now I'll do one that is fair. Let's try this one. If I take this object and put it at, let's say, 20, would you tell me now, according to the lines of light, what's going to happen?
Well, the bottom one.
Bottom one stays, the top one stays.
But the middle one has to be moved again.
Okay.
So move the middle one.
All right, till it's just barely touching and nice and straight. Now wait a minute, you're up again.
Right there?
Yeah, just down a little further yet. Keep.
Down
Yeah.
there?
In fact, may I help you?
Yes.
Because what's going to Oops! I'm a great help. Pick it up, the thing comes off the string. What's going to happen, really, and you'll see why they use mathematics, is that the two are going to come right down there together like that.
They are?
Yeah. See, that's fairly straight now?
Yeah.
But you see how doing it this way, you'd have a great deal of trouble. Let's work it out mathematically and see what happens when you have the object at 20. This time you can do it.
Me?
Yeah.
Well.
I have the formula already written for you. Here you
Mistakes
go.
don't count?
Huh? No,
Mistakes
you won't
don't
make any
count?
mistakes. It's not that difficult.
All right.
First, you're going to put down
Well, that was
minus
1 over 20,
1
right?
over 20 plus,
Plus 1 over 15
right, focal length remains the same.
equals 1 over di.
Right.
So far, so good.
Yeah, very good. Okay, now,
Now.
common denominator?
60.
60. Okay, draw a line. 60.
Right. So let's see, that's negative 3, right?
Right.
And that's plus 4
Yeah.
equals 1
1 over di.
d. Oh, yeah, pretty good.
Okay, now, can you subtract minus 3 from plus 4?
Yeah.
Yeah.
That's 1
1 over 60
equals 1 over d.
Where's the image going to be?
At 60.
60 centimeters, right.
That's why it went to the end.
That's right, it went to the end. And what kind of an optical device is that?
Oh, well, let's see if it...
What's happening to the image now? It's getting bigger
It's
and
getting
it's
bigger
getting
and
further
bigger.
and further away. Okay, let us go back into my dark room again. And you see what we've got?
Oh, the enlarger.
Yes, right now I don't have 60 centimeters on here because I moved it down, but you can run the enlarger up and down to vary the size of the picture. Then you have to refocus here in order to bring it into focus. And after all, here was the original size,
It's
right?
pretty small.
Pretty small, and you've now enlarged it. And of course, you know how they use enlargers. They have photographic paper down
Yes.
here, and they expose and develop an image and so forth. But anyway, now you see how you've calculated that one.
Yeah,
And
it's
here
pretty easy.
here the object is getting closer and closer to the lens, isn't it?
Uh-huh.
And the image is getting further and further away. Okay, let's get out of the dark room now. And go back and do another one, but this time let's calculate it first.
Calculate it first.
Yes.
I don't
All right.
know, it's going to be a little harder.
Well, it might be. This time the object is at 16 centimeters.
16.
Getting closer and closer and closer, right? Calculate
Yeah.
it. Tell me, where will the image be?
Well, soon find out.
All right.
Let's see, it's
Minus
minus 1 over
16.
plus 1 over 15 equals 1 over di.
Now, I worked out the common denominator. It's 240. If you multiply 15 by 16, you get 240.
Oh, that's pretty far. 240.
Yes.
Let's see. Well, that would be 15, wouldn't it?
Yeah, 15 times this is equal to that, so that would be 15 up here. It's minus 15.
Plus 16.
16, right?
Equals 1 over di.
All right. So now can you subtract 15 and 16?
That's 1.
1.
Yeah, pretty good.
Yeah.
Equals 1 over di.
So what does DI equal?
240.
240 centimeters. All right, let's put that on the board once and see if that really works.
But you can't.
Why not?
It only goes to 60.
Well, let's see if we can... I'll move it over here to 16. And you try it. See what happens.
This the one? Yeah, that's the one. Doesn't meet.
Okay.
Not on the board.
Not on the board, but are the lines parallel exactly? They're not, are they?
No,
See, they're
they're getting
slowly
smaller.
coming together. So if we were going to have an arrow that would, the top of the arrow would be out there, way down there,
Someplace over there.
someplace on the
Yeah.
floor. According to your calculations, 4 times this distance, right?
Yes.
This is 60. Okay, what piece of optical equipment is that over here that you use in your everyday life?
The projector.
Yes. Now you can see, making the assumption that all these lenses were the same focal length, which they're not, by the way, you can see now you bring the slide up right close to the lens so that the lens would now project an image up here, and it would be quite far, you see?
Yeah.
So you see how, if you wanted a bigger picture yet, like you wanted to fill up the whole wall, what would you do with the slide and the lens? Where
Well,
would
then you bring it closer.
bring it closer yet? That's right. So it's not very difficult, is it?
No, it isn't. That wasn't so.
That wasn't
sneaky.
so hard. But now we're going to get tricky.
We are.
Yes. And by the way, I mentioned here the fact that that this is not necessarily the same focal length. You could see from our calculations over there that if you did want to have a larger image and you wanted to keep it at relative to the same distance, you could change the focal length of the lens. We've been moving it back and forth, but
Yes.
in this case, this is a 125 millimeter lens. And this is a 50 millimeter, and that was a 50 millimeter, so that the lens's focal length can change too. But let's not get into that. Let's pretend everything's the same focal length.
Okay.
All right, now let's try this one. What happens with your calculations when you have the object at the focal length?
At the focal length?
Yes.
Well, I don't know. Guess it'll be way out there.
All right, try it once. This time the DO is going to be 15, right?
Yeah. That's
The object is at the 15 centimeters.
15
Yeah.
plus 1 right there, right?
Yeah, equals?
Equals 1 over di.
Yes, okay.
Well, that cancels out.
So what do you have on this side?
0.
0. Okay, put 0 down.
Right, so 0
Equals?
equals di.
1 over, yeah, 0 equals DI. How far away is the image going to be?
Well, it'll never.
No image.
No image. at
No
all.
image at all.
Infinity.
Infinity. You could write infinity there, couldn't you? You could put that like that, you know, that infinity sign.
Yeah.
That kind of looks more like spaghetti, but it's supposed to be infinity. Well, let's try it on the board and see if when you put the object at the focal point in front of the lens, at the minus side, does it actually go to infinity on the other side? Try it once.
All right, I'll try it.
I have to move this over, you know, right to 15. Like that. Whoops, and a little crooked way. Okay.
All right, get that out. Right. The parallel.
Yeah, so what does that mean? Are these two lines ever going to meet?
No. But what use can you put that to?
Well, you can't project an image with it, that's for sure, because the two points of light coming from the top of the arrow would never meet, and
Unless you want to see an invisible
the
image.
arrow would be infinitely large and infinitely far away. But you could use this for some other purpose. Let's assume that you wanted to get a nice parallel beam of light like this.
Oh.
Then you could take a lens, and you could put a tiny little source of light at the focal point.
And you'd get a parallel
And
light.
out would come a nice parallel beam of light, just like a searchlight. You know, the kind that go
Yeah.
around like this. Or they used to have flashlights that were made this way, too. They had a lens in front so that while you didn't get exactly a parallel beam of light, you could get one that was fairly parallel. In other words, at least it didn't go out in all directions.
Yes.
Okay. So you don't use this optically because, unless you're talking about light coming in here. This could be light coming this way, too, and you could focus it down to a point.
Yes.
Remember, that's just the reverse of the one I had out here?
Yeah, that's right.
Remember, I had infinity here,
then
and
it
it
came
focused
down.
down to a point. Okay, and now you've got light coming in from all directions in infinity, and you'd focus it down here at a point, in effect. All right, next.
Next.
Yes, now we're going to get a little trickier yet.
Oh.
Let's calculate it first, and then we'll come back and prove it. Come on over here. Because this time,
There's the formula.
there's the formula. This time, what'll happen if we go inside the focal length? Like, let's put the object at 10 centimeters.
10.
Yes. So write down the formula for putting the object distance at 10 centimeters.
How can you put it in front?
Well, no, you can. After all, you can go up and touch the surface of the lens.
Oh, that's right. Yeah.
So you couldn't put it at 10, all right? So this is
All right, so
minus
that's 1 over
1 over
10
10
plus 1 over 15
right?
equals 1 over d I. Well, let's see. A common denominator is 30.
Okay.
So put 30 down. Well, let's see. That would be negative,
Negative 3.
3.
10 goes into 33 times.
and that'd be
Plus
2
2 equals 1 over
And-
di.
equals.
Let's
something's
keep this
wrong.
neat here now.
1 over d.
Why? Nothing's wrong.
Oh, all right. Let's see. So that would be negative 1
Yes.
over 30
Equals.
equals 1 over di.
So where's the image going to be? Negative di equals negative 30.
Then it'll be in back of the lens.
Well, come on around over here. Let me see it.
Well, how can you have that?
Well, now, notice that I said everything on this side of the lens was negative.
Yes.
And I put negative up there. And everything on this side of the lens was positive. And all of the answers you got working out your formulas all were positive, so you figured the image is always on this side.
Yes.
All right. Now, however, suddenly the image that you got is negative, which means it's going to be on this side.
But the light's going that
All
way.
right. Well, wait now just a minute, will you? Gee, willikers. All right. We'll see if we can solve the problem, okay?
All right.
All right. I'll put this at 10. That's where you calculated it to be, right?
Yeah.
Would you please fix that line of light there? Where would it go?
Well, let's see. About there.
All right. Tighten it up so it's straight. Okay. There. No
Well,
image on that side at all.
It's not going to meet.
Yeah, you might as well forget it on your
Forget
side,
it.
right? Okay. But let's assume that we put a big eye here. What's a big eye?
Mm-hmm.
That's an eye there,
That's
see?
an eye.
That's a pupil.
Those are the eyelashes?
Those are the eyelashes. In other words, if you put your eye here, your eye would say, oh, I recognize the lines of light that are coming from this point when I look through, and I'd say that if that's a line of light coming from the point, and this is a line of light coming from the point, I would say that must be, ooh, boy, that's good.
Yeah, pretty good.
And they'd say, well, that's coming over, you know, something like that, and you'd meet, did I make it? That you would see there was an arrow like that. Where did you get it to come out? Negative 30, right? And that's where I draw it. And you see how those two lines come right over here and they meet at a point?
Yeah.
You get the idea?
Yes, but where does that mean?
Come with me.
Where are we going?
Right over here. Look,
The magnifying glass?
look. I'll turn it on. I'll turn on the spotlight in the back. And what do you see?
Oh.
Uh-huh. Let me
Oh,
get it straight
that's
for you.
sneaky.
I turn it down. It's a little bright. There. Now, the object, now I'll pull the magnifying glass out of the way. You see the object is over here.
Yes, it's very small.
And it's relatively small. When you put the magnifying glass in front of it,
It becomes larger.
it becomes larger, but it's not out here, is it?
No,
On this
it's
side,
still in back.
It's on the other side. And if you juggle the focal length, you could get it even larger yet. Notice?
Yes.
As I pull it further away. So now you've just designed a magnifying glass where the image is larger on the other side of the lens and right side up.
It was very easy.
And notice my arrow over there was right side up too?
Yeah.
Very easy. Had you fooled there for a while.
Yeah.
Because you didn't think you could have an image on the negative side. Okay, well, let me turn the lights back on here and turn this thing off. Well, now, while we have kind of oversimplified everything because we assumed all these lenses were the same focal length, in reality they are not. The designer figures out the correct focal length to give him the size image he wants from the original size and how big, far away it's supposed to be. And the other things they do is they have to calculate not only one ray of light, but other rays of light all the way around, and for different colors as well. Because each ray of light, each color goes through at a different, it is bent differently, so that gets very complicated. But they use the same sort of formula that you used over there, but instead of bother to work them all out by hand, which they once had to do, they can put these all on a computer.
Oh, it's a lot easier.
And then they can put the line of light coming in, the computer will automatically tell them where it'll go, and they can use the computer then to help them design lenses, so that they have a little more help and a little more experience.
Yeah.
Anyway. But you did pretty well, at least. You see that when the object is at infinity, on one side the point is going to be at focal point at the other. Well, let's do the whole thing with the magnifying glass over there, and you'll see. Because really, everything that we've done today, you can do with an ordinary convex lens, can't you? A magnifier.
Yes.
When you get a magnifier at home, put it someplace so that you can have one person stand on one side and one on the other. And when you get real close, you're going to see
Oh, big eye.
a big eye right side up.
Right side up.
Right side up.
Uh-huh.
Okay. And now when you move back and you get to...
Gets bigger.
It gets bigger, and what happens to it?
Then it goes out of focus.
Why?
Because you're at the focal length.
Yes, I'm pretty close to the focal length, so the rays are not going to meet properly. And then what happens when I go back further?
Well, you're back in focus, but you're smaller and upside down.
Smaller and upside down, and this would correspond to the projector, to the enlarger, and those things.
Yes.
And what happens when I get way far away?
Well, you're getting smaller and smaller.
And this would correspond to the camera, right?
Uh-huh.
So that with a one simple convex lens, by moving it to and from the focal length, you can represent all the common optical devices. What?